Now, let's start. Okay, so this paper is influence functions for deep learning. So it's basically an interpretability method, but we'll talk about influence functions first. They come from statistics, so they're a statistical model. They essentially show what happens when a model or something changes when a sample is removed. So it's basically showing the influence that a single sample has on a model. This can be the statistics usually uses it for things like
a single sample. Are we allowed to interrupt?
yes,
Yeah. Differential privacy, right? Like the definition of differential privacy is that you have one database and another database that is short of just one element. And
I think differential
that is-
privacy is based on the same.
Yeah,
The same.
that's it.
we will actually get to privacy later and security. There is one of their use cases talks about fragility of models and detecting that with influence functions. So, but yeah, so most interpretability methods have, the popular ones at least, look at how important features are, whether they're per sample or at a global scale. This one, however, focuses on singular samples, which we'll see why that matters later. Okay. However, training a model with all of the samples and then retraining them the same model while removing one of the samples is computationally insane. So these guys developed a method back in the 80s called upweighting. Basically what it is showing how the model changes, how the loss of the model, more importantly, changes as a given sample changes. So their underlying assumption that is that if you perturb a sample, it's essentially the same as removing it. So the original formulation of this is a closed form solution to how this loss, specifically the loss of the model, changes with these changes in any given sample. So this should be done for all samples or just samples you care about, whatever. They define it as so this is the equation for finding the actual upweighting value is the first one. And so this is the inverse Hessian times the gradients. So I'll talk more about the equation later. But the point, as you can see from the second equation, is how you get to the updated parameters as they've been changed with respect to the new Z, the perturbed Z.
So Z is the set, or
Z is a sample. So Z is a
Single
training sample. Specifically, it's a training sample. And so our epsilon is perturbations or changes in Z in the parameters. So
How is this invariant to the kind of perturbation you're doing? I don't see that.
that's what epsilon is. It's delta of parameters epsilon.
On the right, the inverse of the Hessian. Maybe what is the Hessians of the loss, right?
It's the Hessian of the entire model. It's the Hessian of the trained unperturbed models. So that is the Hessian of the model. It's supposed to represent the model in its current state. The gradients, though, are over the perturbed element Z, perturbed sample.
So that is over perturbed Z.
Yes.
Okay.
Yes.
Yeah.
That's their point about the with respect to epsilon, but there are better formulations for it. So the way they describe this is because we don't necessarily care about the loss of the training set, we do care about the loss of the test set. And so that's how they conceptualize this upweighting value is when we change these parameters, so if you see on the first line, we have parameters epsilon. That is the parameters as they've been perturbed as Z is perturbed. And this is, of course, the loss of the test set. So are there questions so far? This is also showing the chain rule because they want to be very explicit that this is for deep models.
I'm just wondering, you're saying like retrain them, initially you were talking about retraining the model, but in this case.
So we can't do,
Right,
yeah, we
no,
can't.
I understand that, but I mean, why are they using the test loss? That's like unseen, right? I mean,
Yes.
like, in the valid.
Yes.
So then why did they use some Z test if they're trying to see what the model? Oh, they're, okay, never mind. Yeah, okay.
It could be easy for training as well.
Yeah, they also,
It could be, the reason they care about the test, I think is kind of obvious, is we don't care about the training, right? We care mostly about the test.
no, I understand that, right,
Yeah.
but I don't see how that connects that to retrain, like initially they were like, to not have to retrain, we're doing this. How does that connect?
Imagine that.
Like, I understand
you were-
it makes sense, but I'm just wondering like how that connects to each other.
Imagine you were doing this with linear regression.
Mhm.
You can just retrain the model,
Right,
the model by removing a sample.
right, yeah,
You know, you don't have to go through all this song and dance. But if you had a test set in your linear regression, if you had, for whatever reason, it would be the same setup. You look at the loss of the test set as you change your linear regression parameters.
Yeah.
Does that,
yeah,
That's what you're saying, Eli, is that strictly usually test data is hold out until you're finally done with all training, right? You don't always, do validate this retraining stuff on it at all.
well, that's the thing, this is not retrain. We don't retrain the model, right? In influence functions, you do retrain it. But mind you, the test loss doesn't impact the changes in the parameters.
no, okay, no, I understand, I think it makes sense too, just from the perspective of like, it's more stable that way to just use it like an unseen sample, otherwise you're just using like a very overfit. You can like get weird.
Yeah.
I was just wondering how that connects to each other.
William, do you want to say something?
I
with this?
can't read that.
Yeah,
Read it to me.
Read what?
No,
There was a comment.
It's gone.
Thought you wanted
William,
to
if you wanna say
something. Read your answer.
Do I want?
yeah.
I guess. I don't know when a good time to say this is, but basically now I guess. So what I'm saying is, I think it would be interesting to see how much. Sorry, I'm a little sick. Changes in change in influence relates to change in weights, because it seemed to be defined in terms of like its impact on the loss. But I'm interested to see its impact of influence on weights. Also, influence seemed a lot like anomaly detection and quantification, because to me it seemed like possibly your anomalies would have a disproportionate impact on your decision boundary and your loss changes.
Not if you
And-
use SVM.
Yeah, I didn't think too much about SVM, honestly. Also I think the another way to get it influence is kind of like if you train with and without the without a specific example, you would see a change in like the gradient for that epoch. And maybe that relative change in gradient would tell you something about impact. But that's all I mean, I pretty much had to say based on my notes.
Hang on, I have comments. So first of all, your point about like anomaly detection or whatever, that's a great point, and we'll discuss that later in the use cases. The thing about the change in parameters, because this is the loss from changed parameters, it's a way to quantify and conceptualize these changed parameters, because we can't with 11 billion parameters, or even several billion parameters, or 100 billion parameters, how do you quantify that? How do you look at those numbers and go, oh, it changed this way? I can't think in 100 billion dimensions. And so the loss is one way to understand that. There are other metrics. I think the loss is fine. I can't think of any other thing. Do another comment.
Gradient shift with and without the sample you're measuring impact for over an epoch. Is that related to?
Well, since this is defined as the derivative, right, as we can see here, that's essentially what we're seeing, right? But it's the derivative of the loss with respect to these changes, and specifically the loss of the test set. So we wouldn't quantify it as the gradients of just the gradient. So let's say we quantify this as just the gradients of our perturbed sample. You can actually see that term in this equation down at the bottom, right? It's the gradients of the loss of, with respect to Z. That is only one part of it. And I will talk about why conceptually that's not what we want next. I think next. Okay, cool. So conceptually, just by looking at the gradients of this sample, with respect to the sample, they're not going to tell us much, right? They're not going to change the model in a way that matters. So if you look at this diagram, you see the actual loss and the quadratic expansion. So this Hessian multiplied by the gradients, the inverse Hessian, actually, that's important. It's just a quadratic expansion of the model. So it gives us the loss as a curve rather than a direct line. So imagine if you just look at the gradients, you'll see this point move from theta hat, which is the actual parameters, in a straight line, which is something we don't want. We want to look at how, because we conceptualize this as a curve, and it's a comment. There is a drill down on that later. But I hope that makes sense. If there are comments, I'm open to hearing them. One thing I glossed over, and I forget where it is. Yeah.
Isn't the Hessian a little expensive to calculate though? Isn't it like the second?
Very much so. Very much so. We will talk about how they do it efficiently.
Okay.
That's their main contribution, I think.
Kind of. So the
Okay.
conjugate. So okay. So let me get out this line, and then we'll talk about how they do it efficiently. So this is analogous to one Newtonian step, which is important because it is that quadratic approximation. But also, it shows us how they get to the efficient computations. Okay. So conjugate gradients approximate the inverse Hessian. So these T are just some conjugate vectors to our Hessian, to our actual Hessian. Because computing the inverse Hessian, the inverse of said Hessian, is incredibly computationally inefficient and a shit show. So we can, though, with conjugate gradients, find an approximation of that, which that's already a conjugate gradients. Gradients are a clearly defined thing. They're old. They're not new. But a guy from, I don't know, like 5 or 6 or 8 years ago, came up with a stochastic estimation of the conjugate gradients by taking samples of your training set. So instead of because this Hessian is this second order derivative over the entire set, every sample. Well, they're like, why don't we just randomly sample at each iteration and blah, blah, blah. And so it works. The authors of this paper had to extend this slightly because that that author only did it for linear models, but, so that is a novel contribution. in this.
Sampling from Z, like the sample space, is that like the training set?
Yes.
Yeah.
Yes. Yes. Sorry, I didn't include the,
It's a little confusing though, to use big Z then for notation, just because they also have Z tests. Like,
so
I understand, I mean, it doesn't really matter.
some of that is my copy paste job. But ZI always refers to a test, always refers to a training.
Right, no, yeah.
Okay. Okay, so that should be clear. Okay, this is. Okay, we will have plenty of time to talk about why this sucks.
Can I
Yes.
dwell on this a little bit more? So why not they using this linear time computation for a motor? Because they're doing, so look at section 3, efficiently calculating influence. Hessian product with a vector is calculated by AD in the same time as the gradient with a constant factor, and that's shown by Barak motor in 1994. So why don't they just use that way? They do mention that it's typically order P.
But is that about computing the inverse Hessian?
It's computing product of Hessian with a vector. It's not inverting it, I guess, but
That
so
might be what
inversion is that.
that might be what they're doing, right? Because if it's just the product, because that's how you can use that in conjugate gradients, can't you? Because if it's just the product between the Hessian and some vector when you're computing conjugate gradients, you can just do the same thing, right?
Yeah, I mean, and it's a
So they
little
might be-
linear in parameters. So, like backprop can do it for us. Okay, okay,
I'm not
anyways,
sure.
so they don't talk about it.
They do not talk about it.
They talk about it as, well, there's this method, and then they move on.
I kind of want to speculate about the Hessian and the conjugate gradients a little bit because like my memory of them kind of comes from like basic deep learning course where they talk about like how you estimate the gradients for back propagation updates, and like a Hessian, if I recall, is like basically a second order approximation. So you could like use it as an update, but people don't because it's expensive. And if that's changed, I wonder if you could update make a better optimizer similar to like, because a lot of like the optimizer upgrades were kind of approaching getting it being like the Hessian. So I don't know.
So on section 3,
Oh, they actually use Barak's approach.
they do.
They do.
So on in section 3, on the last William, on the last paragraph, you can see the runtime of the Hessian.
Yeah.
Basically, probably it's big O of P, maybe P squares. I'm not sure the size of
No,
it.
it should be linear.
Well, if T is big, or if R is big, if they have to, because R is the number of iterations, so if they have to iterate a lot, then it might be polynomial. But I'm not sure. Anyway. This is not computationally, imagine, so you would have to do this per iteration, right? And so that is analogous to one training iteration in your training regime, when you're training the model. So if you want to use the Hessian to update this thing, even if you use their computations, you're still looking at a really expensive thing per iteration, per update.
Okay.
And so that's probably why, even if you, I think you're right. I think there is work on trying to use the Hessian to update for training regimes, but I don't know anything about that.
Yeah, I was gonna say, this is like efficient for like a, or not efficient, but like for an interpretability method, it's doable. But like for training the model, it just becomes so expensive that like, because a training step is like pretty cheap right now. But like then here you would like probably make it like 100 or 1,000 times less like less fast, like depending on how much samples you use for the stochastic estimation, stuff like that. And but if you're doing interpretation, you already have a trained model, so you just have to like run it once and it's done. For all the samples that you have. So it's like one training step, right?
Yeah.
Essentially.
For each. training
Yeah, so one
point.
epoch, sorry, I should say.
Yeah, one epoch.
Yeah, it's like the same as one epoch, but then it's fine, because then you're not doing it for 100 epochs, you're just doing it for one.
Okay, so. Something. Okay, so I think the method itself makes sense. We'll talk about the use cases. This is, I think, where it excels. One of their first, maybe their first actual case, their important one, is looking at the security of these models. And they show that you can basically develop adversarial samples really easily based on this influence function. So and what they showed was like really highly accurate and effective samples. And so that's a problem, right? If we have classifiers in especially the medical field, and you can easily craft adversarial samples, I think that's a huge issue.
Or if you have a model that's trained on outliers, you could potentially reconstruct an outlier, which is a huge thing in like small populations of.
Absolutely. Yeah. And that actually aligns with their second use case, which is domain mismatch. So maybe the trainings, maybe there are outliers in the training set that don't exist in the test distribution. And that's one of the benefits of using the test loss, because it shows you the changes in the test distribution, which is supposed to be the real life distribution. But by doing that, they can find training samples that do not belong for whatever reason. And that again feeds into maybe these samples that do not belong, which is to say a sample that is highly influential. It may actually be mislabeled. Again, this is another issue in the medical field. If we have, because we often have small data sets, right? Anywhere from 10 to only a few hundred subjects. But often they can be mislabeled. There's plenty of cases of misdiagnoses, all sorts of issues, bad paperwork. And so this would be one way to help look. Let me actually step back. The idea of influence functions is not necessarily to understand the model, but to help explain parts of the data. And so that's, I see it checked.
Is that checking out another paper might be useful?
What's the name of that paper?
Also, one thing I think I saw on Twitter recently, a paper that showed that actually the most influential samples are often the ones that are misclassified.
Let me.
Yes.
Yeah, what I'm interested about, I mean, even though mislabeling would be bad, but what if like the rare events that are important in our small data sets, like tumors, like what if they're highly influential? And you don't want to.
Well, they would be highly influential in that they decrease the loss, right? But if it's mislabeled, it's going to increase the loss.
Okay.
Mahfouz, maybe you can tell.
This one.
Yes. You had a
Oh,
comment.
this paper actually, I gave some very brief highlight about this paper on some other day, right? This paper actually does the similar thing, that what is the influence of the training data on the ultimate model.
What is the name of the paper?
Yeah, I already typed it.
Can you post it in Slack?
Yes.
Frankly, I would prefer all of our comments in Slack in the meeting group.
Yeah,
as
sure,
people,
sure.
because then they will remain there as a
Okay.
thread to, instead of here, they kind of change the flow.
Right. Okay, Noah, go ahead. I'm just I will be just posting in the channel. Okay.
Thank you, yeah. Or interrupt.
Yes, actually, yeah, feel free to interrupt. Let me go to,
Predicting predictions from training data.
predicting predictions. Okay, cool. Yeah, I have not read that paper. We can talk about it though. Because this is essentially the methodology and the purpose of this paper. So the methodology is already, you could say, sound and well-worn. We've been talking about influence functions for, I don't know, half a century now, at least in the
I don't
context.
think this is all. I think like it's also the interpretability, the kind of the feel good thing. The human doctors and any professionals, they need to feel they're in control. So when you show, okay, I'm making this prediction because those are the, like, that's how we teach each other, right? It's like, look at the use cases, they're like that. That's why this person is more likely like that. It is not any of the three.
But it doesn't necessarily tell us about the subject, right? Because it's only a value per subject. It tells us that this subject
Is the most
Is
influential for this
Yeah.
prediction.
So
And that-
yeah, that's a good point. It will, in the example of a medical field, it will tell practitioners, which it will tell the users of said model what subjects to investigate.
Or like what training data influence that prediction, you don't need to investigate, but it's like, why are you saying they have cancer? And
But
they're like, okay,
That's
well,
the thing, it doesn't say, it doesn't give us the why.
it does, it says, well, because those the training exam.
Not
It
necessarily.
doesn't do anything to like salience does, where it's like.
Yeah, because it doesn't
space
give-
of the-
It doesn't give us, exactly, it doesn't give us a value per feature, right?
No, I don't care about feature, but it says, like, it gives us a case. Here's another subject that is just like that influencing my decision.
Yes,
That's
but
it.
I would say that the practitioners, the users would have to investigate that. Like if they find several patients who are highly influential, they want to know why. So they would have to investigate that themselves, that's a good point. Because it doesn't tell doctors what, it tells doctors where they should look, which I think is a healthy balance between models that just tell us all the answers and we go, oh, look at the. And instead, the model's assisting us and helping us kind of narrow down the scope of where to look. But it allows the doctors, practitioners, and the users to use their own human understanding, their own human knowledge or
we can
intuition.
help them further with saliency maps of those most influential samples, for example, and the test sample, and there is infinitude of like how deep we can dig. And
Yeah, let me get Bean Kim on the phone.
yeah, okay, should I dial or you?
I have her on speed dial. She's not. She is the greatest interpretability researcher currently. I just want that to be in the audio waves. Anyway.
Well, he's interviewing in the lab next
by the
week.
way.
I know, I'm. Okay, anyway, so I think that's pretty much, are there comments about this? Because otherwise we can dive into why it's garbage.
It seems, I would just like to say, the way that y'all discussed interpretability, it seems like really at its core is a need to understand causality and an expression of frustration of current models' lack of ability to relay this. Because like you ask a doctor, why am I sick? He takes an MRI and he can find a tumor. Like at least he knows where it is. And he knows a lot about tumors and stuff. But like if you have just a model that spits out you have a tumor, but we don't know where, that doesn't help you if you don't have a well-educated expert around.
So ideally, interpretability would teach us about the data. However, the models themselves often pick up spurious correlations. So the models may not actually know why somebody has cancer. They may just know that there is something correlated. Like maybe pictures of brains have a tag that signifies. I can't read that.
Me neither, I just tweak.
Can you?
Cause arrow, feature arrow.
So we have feature prediction and cause. You can say, okay, well, you have prediction, diagnosis, and cause. Go figure the connection. The model gives a, like some causal relationship generates the data, leads to the data. There is a data generating mechanism from the causal mechanism that William is talking about, and like how the data looks. And then we'll look at the data and make a prediction. So now what William says and what we want is from prediction, how to go back to the cause. But that's kind of difficult because there are too many. So the model at least can get us back to the relevant features here. They're correlational, but I'd like ignore the noise and stuff.
So ideally, it can get us back to the feature space, ideally. But
To the data space, I don't know if we want, if you care about.
I mean, data, I guess.
Sure. I get your point. And that is the ideal case. However, we do know that these models often pick up spurious correlations. We also know that different random seeds will lead to different models, which of course leads to different interpretability maps. We also know that a lot of methods, which if you want, I can spend the next several hours talking about this, but a lot of methods, interpretability methods, have certain flaws. Dr. Kim actually showed this a couple months ago. Importantly, she showed that a lot of the visual methods, saliency with gradients only, integrated gradients, actually have trouble picking up on known spurious correlations. Their experiment was, hey, let's tag a bunch of images of, I think it was like X-rays or CT scans of skeletal fractures. And let's actually tag them as the given class. And the saliency maps, both saliency, integrated gradients, whatever, did not necessarily pick up that correlation. It showed that it was somewhat relevant, but not as relevant as it actually would have been. So these methods,
They like physically wrote the label on the image. So
they tagged it, yeah.
Yeah.
And then their second experiment was a Gaussian, they just Gaussian blurred, so we couldn't see it visually. But of course, there was a Gaussian blur.
But did the model use that information? How do we know?
It did, that's what I say.
No, the model did.
Oh, the model did.
Yeah, they showed that later in the paper, but the model did. But the method itself didn't pick that up. And especially in the, there's nuance. In the physical tag experiment, it did pick up that, hey, this is important, but it may not have shown how relevant it actually was. The second experiment, which is where they added a very not visual Gaussian blur to one class, there was almost no correlation to the blurred area, but they knew that that blur was impactful on the model. So there's that, and although I would say that that is maybe one of the most important flaws in these methods, because we often use these methods to understand when our model is wrong. And if they're not good at that, well, and that's a problem. But of course, there's so many other papers that show that these methods have issues. So your point of, will we get back to the feature space? Sure, we can get back to the data space. But what we get back might be incorrect, both because of the model and the interpretability method itself.
And if that's incorrect, it's even harder to get back to cause because.
And then I wouldn't even dream of talking about the cause based only on interpretability maps.
I think your interpretation of interpretability maps is very narrow.
Yes.
Like it's very specific to saliency maps, to the gradients based.
So there are other methods. SHAP. SHAP is effective. It has its own flaws. But yes, there's plenty of other methods, right? Deep lift. We don't need just the gradients, but most of the experiments have been on gradient based.
Use they're easy to calculate, yeah.
But there have been experiments on SHAP that have shown that SHAP has its own flaws. And intrinsic interpretability, like attention, has its own issues, which I think you know, right? So,
I
yes,
think it was recently a paper that said like, attention is not at all showing the actual attention of the network or something.
yeah,
I think that it's actually just like, not at all what it is attending to, it's just.
it's often really noisy, which says something that because it's intrinsic to the model, that does say something about the model.
Right.
The attention values themselves don't. It's not
Yeah.
what we invented them.
I don't
Yes.
want to continue to interrupt so much because we're probably, I don't know how much time you need to finish your presentation, but
It's
one
all
last
right.
idea, I guess, I'll throw out there is for interpretability that came to mind is that like, if you're working with MRIs and you know that there's like a presence of like some disease like Alzheimer's and you get flagged in such a way, then like how much would you have to warp the the thing that has been tagged as one class before it becomes normal, flag that warping in some way that like you can see the location of what changed and then that show that to the expert. I don't know.
I'm sorry, I'm not sure I understand.
Yeah, it's probably too.
I can try to explain what I understood what you were saying. Well, you're saying like they just say perturb data. That's something you can change, right? Is how you perturb. So you're saying you could warp data in different fashions to different degrees and see, over what boundaries in terms of your perturbation function actually get high significance with this metric, for example. And so that might give you information about the data based on, so if you
That's a good point.
warp a subject so much that they, it looks like they have a lesion in their brain and then it identifies them as having a lesion.
That's it, yeah, that's William, that's a good point.
Yeah, it kind of reminded me of like fast gradient sun, but like if you could just like if you have a if a certain data example has like a problem, but you don't exactly know what it is, like if you warped that example back to being normal and then you flagged what changed, then you would like have some like heat map of like what needs to change to make this person
With like the augmentations and stuff.
But static maps are sort of trying to get at it, right? It's like how Marcuse was experimenting with what is the
Integrated gradients?
no, remember this model that everyone liked when we didn't know anything about deep learning? Inception. Yeah, Inception. When you change the data until it becomes a different class, but the gradients are pointing you where you should be changing so it becomes a different class. So that's exactly what William is getting at.
But a lot of it currently is like residual tax, it's just like very super tiny little bits of noise you can inject.
Yeah, they're very
decision. So I don't know how much that actually like shows you what is the cause or something. It doesn't tell me anything. If I can just add noise and it's a different class.
No, but Inception was like on a larger scale.
I know, but even now with modern models, you still have like, I don't know if that tells you anything. Oh, you can inject this noise and it's a different class. Does that tell me anything about the class? I don't know for sure. I don't think so, actually. I mean,
Yeah, I think it tells you a lot more about the flaws of the model.
right, that's what exactly. And I think that's also what Noah's kind of saying is like, does it tell you something about the data or does it tell you something about the issues with the model? Like, that's the question when you map it back to feature space, right? Is like, where does this come from? Is this because the model is just overfit or picking up spurious correlations or doing all these types of like weird things? Or is it because it's actually something in the data that's like wrong or like different?
Yeah.
One thing we see a lot in MRI is masking voxels, right? It's a kind of perturbation, right? Trying to find significance of regions and ROIs based on if they're masked or not, and if they don't, so it's one to look out for.
Yeah. That's a good point. Okay. So,
What's your next slide? No.
there are no next slides. It's just me
Ah.
talking. So there's another, this is the wrong one. There is another paper that talks about how influence functions are actually quite fragile. They actually use the term fragile. And their first argument, like right out of the gate, their first argument is influence functions assume that this surface is convex, right? Because it's quadratic. So, but that is probably, maybe, in some cases, a wrong assumption, right? In ResNet, we've seen that they might probably be convex. Or no. There's a thing called visualizing loss surfaces.
No, I've seen the paper, but I think that was locally convex, not completely convex.
All they did was they took the loss surface and condensed it down to like a very small space and showed that small space itself was convex. So even though there might be, I think they framed it like this, there might be locally non-convex spaces, but that the surface itself is mostly convex. And that they could not find the possible locally non-convex spaces.
Are you talking about saddle points versus actual local minimum?
You know the paper visualizing loss surfaces?
Yes, 2018 new release.
Yeah, oh. Look at the memory on you.
No, I was there.
Oh.
I saw them though.
He was in the lost.
Yeah, I was lost in the lost house. And suddenly it became convex and I was just like, oh, it's a slide.
So resident sapien. Yeah, so this other paper, which is posted in Slack, so if you would like to read along with me, we can do that. But yeah, that's their whole point. And it's so that I think is an issue. To make the assumption that a given loss surface is convex is erroneous. So even though these influence functions by just the use case can show us something about the model, they can show us something about the relationship between the data set and the model, the assumptions are really heavy and possibly wrong. This other paper, which I have not actually finished reading, goes into other experiments. I think Kevin brought it up. But it again points to this story that we're seeing, that interpretability methods, along with the models themselves, have a lot of flaws. If the interpretability methods themselves are fragile or unreliable, or they have very key flaws, that makes the whole field very shaky. And I would say that, because right now, look, this is my diatribe, so enjoy this. Right now, we are racing to develop new interpretability methods. We publish a new one every day, and some of them might be good. Some of them, I have not published a new method. I published a fix.
Every day is that.
Yeah, every day actually. Every day I publish.
He did say we.
In my
head.
In my. Yeah.
Honey, I have to publish my paper before tonight.
I gotta upload it to Noah Archive. And so in this race to develop new methods, I think we're missing that these methods, which many of the new ones are based on gradients. So we already know that there are these huge plot holes. And if we're not rigorously experimenting with these new interpretability methods, it becomes like, well, how can we trust them? If we can't even trust well-worn methods, how can we trust new methods? Which I think speaks to the field itself, and that we should, the field of interpretability, and that we should probably take a step back and think more about what our actual goal is. If our goal is to understand, and this actually I think is important for our lab, because our goal is to understand the data. We want to model the data and then we want to use a method, post hoc or not, to understand the data, and interpretability should give us a good avenue. And if that's our goal, then we should be hyper-focused on that and be very careful about the kind of interpretability methods that we want to use, because they need to be very clean. They need to be free of their own noise, in my opinion. And they need to
I'm
be
just wondering what do you mean by clean?
free of their own noise and free of model noise.
Which there's some papers that are currently coming out that are trying to do this, like redefine exactly with like axioms and theorems what interpretability is supposed to be, and then like,
Yes.
you know, because it's a little bit hacky, a lot of methods, you know.
Oh, but there are many ways. I am against normative approaches. That's why I kind of suggested this paper, because this is yet another way to think what is interpretability instead of the map, the samples that influence your prediction or.
And of the methods that I've seen, this one seems actually kind of elegant and beautiful in how it operates. Because I personally believe that if you're in the medical field and you want to understand why someone has cancer, so let's say an AI says this person has a brain tumor, and you want to understand why, I suggest that the doctor should be the one to answer that, not the AI itself. The doctor should be the one to say, oh, the tumor is here. Because the AI has already so many known sources of noise that it's like, well, how can you really say that the why, that the cause is correct?
Have you seen this GPT-3 Literary or like the open source version explaining jokes and like giving you? It's kind of.
Or the one that also explains sarcasm and, oh yeah, I've seen that.
But there was also recently another paper that showed that it has no idea how cause and effect works, and it can
Of
do
course.
no relational inference.
Yeah.
Which that's, I think, also the problem with like training neural networks under everything, right? It's very hard to know whether it has any idea about the relational, you know, between, does it understand, like, you know what I mean?
Well, but that's a question of Chinese room, right? What do we want? Do we care if it doesn't understand, if it gives us explanations that are correct? Like.
Well, but can it give correct explanations if it has an idea?
How do we know that the explanation is correct?
Right, that's the also good.
I have to play the devil's advocate here a little bit. I think Noah has a great points in that current generation AI probably can't even come close to replacing the expert level knowledge of a doctor. But I don't think that future generations of AI will necessarily, that will be the case. What happens when AI is actually able to figure out causality better than researchers? Do you still want the inferior explanations?
Isn't that the
the
goal of AI, just to, you know, to understand what we might miss initially? So I feel like that it's a good thing if AI is able to understand the causality or even the relation better than human beings, and at certain, just a certain.
Well, and if it can understand it better, then it can explain it too. And that's something that we should be wary of and build into those models. Like if it can find those causalities that we may not be able to find, or it's very long for us to find, I mean, we need to make sure that it can explain to us why it's doing that, because otherwise it will spin out of control, obviously. Like that's the whole point of interpretability as well, is like, you know.
And that brings up the point of, okay, so we have to understand the model. Can we do it reliably? And if our current methods are flawed, maybe the idea is, let's understand the model from multiple angles. I actually argue that instead of just like, oh, I did saliency maps on a thing and this is why I did the thing. Why don't we amalgamate all of this? Why don't we use influence functions in conjunction with saliency maps, in conjunction with.
But your diatribe started from me suggesting that. I thought you were against that.
No. My diatribe was about not inventing new methods, but instead using a.
How could you know?
Yeah.
Not inventing new methods. How can we leave them?
We should
We can invent new
de-invent.
models.
We should de-invent. We should get rid of our current technology.
There are kinds of people that like to fight, for justice. There are kinds of people that like to build and things like that. But I want to interject there about
Yes.
understanding. I was kind of listening to Eloy about understanding. What is understanding? And I think, or understanding or causality. We're very binary in our conversation right now. That either you understand, whatever that means, or not. I argue that until like maybe 50 years, the humanity, we didn't understand things. We just put the metal into fire, put this block into water, and then like, okay, it will be stronger metal. Did we understand? Well, no, we didn't understand the phase diagram of iron and C, whatever, the carbon. We did not. But yet we understood that if we do this, there will be, that's
Yeah, but
also
that's
kind
not
of
what
understanding.
Yeah, but that's not what neural networks have though.
No, they don't, but there is what I'm trying to say, there is a degree. Neural networks don't forge metal, they don't do that, or like whatever, but whatever they do, there is a degree. Reinforcement learning may have some actionable things, but there is a degree to what understanding means, and it's not always.
So the way I think about it is like if I was teaching a student and when they just write down the answer, you don't know if they've actually understood the material, right? And it's the same with the model. If it gets high accuracy, if it produces the right output all the
Well,
time.
it's
or
consistently
wrong
the
output.
student writes down.
Yeah, but maybe
But you don't know if they've actually understand the material. And what you do is probe with additional questions. You probe in all these different ways. You don't maybe look at their neurons, but you do this comprehensive analysis to get at what the student is actually understanding and learning. And I think we need to do the same with neural networks, and that involves, comprehensive sort of teaching and validation suite, rather than.
But we shouldn't expect like the complete causal understanding of the universe or
No,
even the
but that's just
domain.
what I'm saying. Yeah, it needs to just know that it's making this prediction based on the fact that it sees a tumor. That's not like rocket science. That's like something that we also do.
No, but it may
Sure,
make
there's a
us.
degree of understanding. They could also understand the complete process of how tumors start. I'm not saying that is what I mean by understanding. I just mean what we find to be the reason it should be making the classification. That is, to me, is understanding. That's where it starts, and then it can be further than that. And sure, it's a whole scale, but like I feel like relational explanations need to be, they're important when we put these AI methods in like an actual setting where it should make these decisions. It needs to be able to explain to us why it's doing these things. And I don't think, currently we're there yet. Like it's not good enough for a lot of things, at least. And sure, it's better to use a lot of different methods to understand why it's doing something. But obviously the holy grail is if we can just explain to us why it's doing something.
I think what's would be important to be afraid of, at least, is like quality of care. Like there's a push towards like making our models widely available at the expense of quality of care of certain individuals, and you got to ask yourself, like, is the quality of care of certain individuals over a mass increase in care overall? Like, what's the trade-off there? What are you losing? I don't think there's any chance that we're going to replace doctors immediately. It just doesn't seem to happen that way. But I do think we might replace them slowly. And
that's also not true. I mean,
so,
you need FDA. Like the FDA is going to stop most research on this anyway because you can't interpret it. I mean, they only had one interpretable diabetic retinopathy algorithm in the last 10 years go through out of like the dozen that they had to go through. So
what's not true? I didn't understand what you meant by what's not true.
I mean, you just said patient healthcare is going to decrease, correct?
I said it might if you push through things that aren't as good as the doctor.
But what I'm saying is the doctor will always be involved, at least in the next 10 to 15 years.
That's also, I also just said that. I basically was saying that, like, I said in the short term, I don't think the doctor's going to be replaced. Like, for example, physician's assistants are basically an example of attempts at kind of increasing widespread access to care, but potentially decreasing quality of care. I think that AI models and stuff will basically be a further instantiation of this, like taking care even more widespread, but possibly decreasing quality even more in the short term. But I think eventually,
Yeah, we're out of time, that's what I'm trying to.
I also don't think it's gonna be as common in hospitals as people think, because doctors are like, they really push back against these types of things, like, they wanna understand it, but there's not like, you know, because doctors, like, some doctors like it, but I think a lot of
push back,
doctors
but
are also
insurance
very like
companies don't.
critical of like, no, just what is shown. No, not the doctors, no, that's the
Yeah,
hospital,
wait,
that's the hospital,
so online, people, thank you for joining. We have to, it's 11:04,
I don't know.
1:04, and I have a meeting at 1. I have to go, thanks. Next meeting is Introduction to Lifelong Supervised Learning. Let's see. I forgot who is presenting that paper. but See you next Friday. And there will be pizza probably next Friday at this time, so come in person if you can.
We do it all the time.